we're going to look at a certain kind of differential equation, a separable equation. A differential equation is an equation that contains a function and its derivative. I suppose I could say potentially plural derivatives. For our purposes in this section, it will only be a first derivative. Right off the bat, I'll give you an example here. Y prime equals 3xy is a differential equation. We have the function y, and we have its derivative y prime. Our goal is to get an explicit expression that defines y without referencing y prime in it. Given an equation that looks like this, the first thing we're going to do is write it in Leibniz notation. Dy dx is equal to 3xy, and then use the fact that first derivatives act like fractions to get everything that has a y on it on one side and everything that has an x on it on the other side. So now we have dy over y is equal to 3x dx. With the differentials on both sides, it should make sense. We're going to integrate. And on the left-hand side, what we end up with is the natural log of y, really I guess the absolute value of y, is equal to 3/2 x squared plus c. We're just using integration rules that we already know. If possible, I should have said if possible, we're going to isolate y. If possible, we're going to get y by itself. It's not always possible, but in this case it is. We're going to exponentiate both sides, and we end up with y is equal to e to the 3/2 x squared plus c. And then looking at the sum in the exponent, we're going to consider that to be a product. And finally write down that y is equal to, we'll just change that constant a little bit, k, e to the 3/2 x squared. Now this plus c becoming a k, we're going to get into that later. But the point here is that we had a differential equation, and we were able to separate it by putting like with like in terms of variables. And then using antiderivatives, we were able to write this equation here in such a way that no derivatives appear. This was actually a separable differential equation. What characterizes it as a separable differential equation is that it can be written as a product of a function of x and a function of y. For instance, dy dx is equal to f of x times 1 over h of y, which you might also see as f of x over h of y. And it's separable because we can get all the x's on one side and all the y's on the other, like we just did. So here we'd have h of y dy would be equal to f of x dx. We can then solve the differential equation by integrating both sides. H of y dy in an integral would be the integral of f of x dx. Denoting the antiderivative of h as an uppercase h of y, we get h of y plus c1 is equal to uppercase f of x plus c2. But what we typically do is combine the two constants and just write h of y is equal to f of x plus k, and in this case k is equal to c2 minus c1. With this in mind, let's look at another example. Dy dx is equal to x times the square root of y. Almost left out the instructions there, which would be solve the differential equation. Well, separating our variables is going to give us dy over the square root of y is equal to x dx. I'm going to want to use the power rule, so we're going to express this as y to the negative 1/2 dy is equal to x dx, and at this point we're going to bring in our integrals. We just need to find antiderivatives on the left and right. Using the power rule is going to give me y to the 1/2 times 2 on the left-hand side is equal to 1/2 x plus c on the right-hand side. I think I said we're going to use k, so we're going to say 1/2 x plus k. And we'll say if it's not too bad, solve for y. We can do that here first by dividing by 2 and then squaring both sides. So y to the 1/2 is equal to 1/4 x plus, I don't really want to write down k over 2 since k is just a constant. So I'm going to call the k that we already wrote down k1. And then now I have 1/4 x plus k, where k is actually half of k1, but to tell you the truth, nobody really cares. Here's what folks should care about. Did you catch my mistake here? I didn't use the power rule on the right. We should have 1/2 x squared plus k1, which then leads to 1/4 x squared plus k, and that equals y to the 1/2. Squaring both sides is going to give us that y is equal to 1/4 x squared plus k, the quantity squared. That solves our differential equation.